Hello, I'm Alan Bates, and I'm here with you today to talk about an experiment to measure the speed of sound in air. It's no ordinary experiment because we use three different techniques or approaches. One with the Pasco motion sensor, another with the Arduino microcontroller and ultrasonic sensor, and the last approach will be using the Phyphox smartphone app. I want to just first talk about this equation. This is the equation that's typically used to measure the distance to a target, and that's what ultrasonic sensors, motion sensors, typically do. They take the speed of sound in air and they multiply by the echo total time, ping echo time over 2. It's important that this time is divided by 2. But most importantly here I want to say is that the speed of sound in air is assumed to be a certain constant value. Some systems allow you to change that, but generally it's assumed to be fixed, but we never consider the effects on temperature, so it's not 100% accurate, but that's acceptable like all measurements. However, I want to approach this experiment in a different way, not to measure the distance to a target, but actually to measure the ping echo time and use that to get the speed of sound in air, knowing the distance to the target. So as I said earlier, speed of sound does depend on temperature, so it's tricky to assume that this is a fixed quantity, 340 around. So yeah, let's talk about the three different approaches. So as I said, it's with the motion sensor, Pasco, with the Arduino microcontroller, and with Phyphox. So let's start with the Pasco motion sensor. Now, as you see in these images, I'm using kind of an older generation sensor. It's the Passport motion sensor, which is the Pasco one, with the AirLink. I just want to say that you could also use a USB link. The Bluetooth adapter is not necessary, or you could also use the new generation wireless motion sensors, Pasco's wireless motion sensors. So they would all work here. Now you can see the setup. If you see on my screen here, you've got like the distance from the sensor to the target. So I'm just using a rigid piece of cardboard, a ruler. And in this experiment, I measure the ping echo time at two different distances. And we're going to see that in a second. So, and there's just another image of the setup here. Now, Pasco Capstone gives us lots of possibilities. I just want to guide you through this. I'm going to start this video and just bear with me as I go through all the steps. So you set up a position time graph. Okay, the sample rate of 20 Hertz, that's just fine. Now we set up recording conditions. I just time based. And I want it just to time out after 5 seconds. Okay, now you can also pick some statistics. We'll talk about that later. And we're ready to go. So we record data. So I've got the target 30 centimeters in front of the sensor, and it stops after, the recording stops after 5 seconds. Okay, now I'm going to move the target to 80 centimeters. And just repeat the measurement process. Okay. Now, so we know the distances. We fix those distances. You can actually zoom in here. Show both runs. And you can see that there is a difference. Okay, this is expected. Now, what I like about the Pasco software is you can do a lot of, let's say, different calculations. Now, what I really want to bring your attention here is in the motion sensor setup, you can see that in calculating the distance or measuring the distance, it was assumed the speed of sound in air is 344. So we know that that's what the Pasco sensor has that programmed to be. You can change that also. Now we're going to use the calculator to add a new function. And the first one I'm going to calculate is the echo time. Now we know that speed is distance over time. So therefore time would be distance or position divided by the speed. Now, since we know the speed of sound in air for this sensor, as we saw in the setup, is 344 meters per second, this would actually give us the echo time, because that's what the sensor is actually measuring to calculate the position. So all we're doing is just rescaling that measurement to go back to the original raw data of echo time. The next step I want to do is calculate the difference in echo time, okay, between the two measurements, okay. At 80 centimeters, that's run 2. And I subtract the echo time for 30 centimeters, which is run 1. And I put in the unit here. So that's my difference in time between the two targets. Okay. Now remember, the echo time is not the ping echo time. It's just the time for the signal to come back from the target, okay, to the sensor, or from the time for the sensor to the target, sorry, the time for the signal to go from the sensor to the target. And I get the speed in sound and air because I know the difference in distance between 30 centimeters and 80 is 50 centimeters or half a meter. And the speed would be distance over time. But it's this difference in echo time. So I use that then to put the unit in meters per second. So now I can actually calculate that. I think it's really important to emphasize that the echo time is the raw data here. So the great thing again about the Pasco Capstone software, I can show the difference in echo time, which is no surprise. Okay, you can see the 30 centimeters below and 80 centimeters above. And then this is the difference in echo time, I should say here. Quite a bit of statistical variation. But most importantly is, I love this, is you click here, you can plot the calculated value of V. And you can see the mean value is about 348 meters per second. Fantastic. There are lots of nice features with Capstone, with statistics. We can do the max, min, and standard deviation, and you can get a pleasant color-coded standard deviation. So if you actually stand back and look at this, we have a mean value of 348 meters per second, and very little deviation there. So it's fantastic, and you can see the color coding as well around the mean. So this is quite an expected result around room temperature. Okay, so I'm going to soon move over to the next approach, which is with the Arduino. And I just want to take a few moments to, excuse me. Okay, now I'm going to move on to the Arduino sensor. And I'll just go to the next page here. So this is a homemade sensor. Again, I had plenty of time over lockdown to kind of play around with these sensors. And it's inside, you can see it's an Arduino Uno board. This is a kind of not from Arduino, but a typical, an equivalent board. I put a small piezoelectric speaker in here for every time you want to collect data. It beeps at every kind of measurement process along the way. We've got the ultrasonic sensor here. And I just include this to the box and just to hit the electronics inside the box. And this is our cable USB that we're going to connect to our laptop to record the data. Okay. Now, just to let you know, this experiment is in a slightly different way compared to the last experiment with the motion sensor, the Pasco motion sensor. What I did is I varied the distance, the target distance, from 10 centimeters to 100 centimeters. And you can see here I'm varying. And I measured the total kind of ping echo time. So that means the total time, transmission, receiver time, up and down. Here I use the Arduino coding. I basically programmed a microcontroller. It's quite straightforward coding. There's a library that comes with that sensor, but I added a few features to kind of make it user-friendly for students to try. And this is kind of an interesting project because it brings in a lot of STEM skills. There is coding, but there's the idea of making an interface for people to try. So you essentially just measure the ping echo time with this subroutine here. And there's a special library for this sensor. And what I did is added a lot of text to guide the user through the experiment. Here I put in the possibility that your starting distance in centimeters, your end distance, so from 10 to 100 centimeters, and in increments of 10 centimeters, and a delay of 10 seconds between each trial. I want to show you just the recording stage. I might fast forward a bit near the end, but this is the concept. That's the serial monitor you open in the Arduino IDE. And this is the text I put in, so you get ready. So I have the target 10 centimeters in front of the sensor, and it's measuring the time, ping echo time, in milliseconds. Again, there's a 10-second delay to give the student or user a few seconds to get ready to move the target 10 centimeters away. And again, you can program this. We can see it's not exactly a doubling in time. These are experiments. Okay, I'm going to just fast forward a little bit. So it basically repeats this. You go all the way up here to 100 centimeters, 1 meter. I'm going to just stop. So this is your raw data. You can select, copy and paste, put this into a spreadsheet, some of the graphing software. Important to note is the distance in centimeters and time is in milliseconds. Okay, I'm going to just go to the next page and just explain the data analysis. So here I plot a graph of the ping echo time on the y-axis in milliseconds against the target distance in centimeters. And I did a linear regression, a curve of best fit or trend line, and you get a gradient of 0.057 milliseconds per centimeter. When we convert it into SI units, we get 0.0057 seconds per meter. Now, a quick analysis tells us that the speed of sound in air will be twice the target distance over the ping echo time. Rearranging for a y and x variables, we get that the t is 2 over v times d. I put this in y equals mx format, so we can compare this equation to the equation of a straight line passing through the origin, and we get the gradient is 2 over v, or v is 2 over the gradient, which results in a value of 351 meters per second. So again, just to emphasize how you take a sensor that's typically used to measure distance, and assuming the speed of sound in air is a fixed value, instead I fix the distance and measure the time to calculate the speed of sound in air. So we get a similar value, 348 meters per second for the first approach. We have 351 meters per second for the second, and these were conducted on the same afternoon. Now I want to talk about the final approach, which is using the Phyphox app here. This is an app I just discovered recently, about a year ago, thanks to a friend in the AAPT. And so the Phyphox app it's an app I just discovered a little bit under a year ago, thanks to another member of the AAPT for sharing this with me. And it's not perfect, but I like it because it's basically so available to students and teachers at zero cost as well. As a sonar timing function, and essentially just sends out an audio sound, it measures the reflected sound and estimates well, you can use it to get distance, or as I said, you can go back and get the ping echo time, and then from there you can work out the speed of sound in air. So it's a similar approach to the other two experiments. So not measuring the distance to the target, we're actually measuring the ping echo time. So it's a sonar timing function. And I just want to show you a typical graph that you can capture. You can export data to spreadsheets. You can actually remote control your smart device as well through another device. And this is typical. I had a target distance of 0.5 meter, 0.5 meters. I didn't do I did a different data collection to the other two experiments, but just to demonstrate what you can do with this sensor. It gives you distribution of times. I went for the peak time, because there are reflections from other surfaces in the room, and it's very difficult to eliminate them. But it's an interesting instrument, an app to explore. I got this 2.771 milliseconds as my ping echo time, and using this target distance, I worked out the speed of sound in air at 360 meters per second. Slightly higher than the other two, but still with lots of potential as an instrument also for other types of experiments, not only sound, or many other possible measurements with this app, not only acoustic. So just to summarize before I finish the presentation. So in summary, just a comparison of the values for the speed of sound in air for the different techniques. Again, the outcome, the aim of each of these experiments was to get the speed of sound in air. Slightly different approaches. But what I like is that there is room for students to explore. There are lots of different possibilities here. So in summary, we have the speeds of sound. In summary, we have the different values for the speed of sound in air, experimental values. And this is just simply a comparison of the three techniques. Different approaches, different technologies, but lots of room for creativity, individual approaches, open-ended investigations come out of this as well. There's just many possibilities. So I just want to wish you all well. Thank you for listening, and thank you for AAPT for hosting my talk. Thank you, everyone. Best wishes. Bye-bye.